For question 3, this is going to be a question on our ideal gases. You can see quite clearly volumes, pressures, temperatures, etc. And it even says the word ideal gas at the end of that first section. So I've got my data booklet ready and waiting. Let's get going for it. We've got the mass of a helium atom is 6.6 times 10 to the minus 27 kilograms, and we want to estimate the average speed of the helium atoms in a container. Okay, to do this, we need to be linking our temperature to our energy, and we can see the data booklet. We've got an average kinetic energy of 3/2 times the Boltzmann constant times temperature. Temperature's got to be in Kelvin, so we'll just do a quick check. Absolutely, we're in Kelvin, so no worries there. What follows is simple working through. We've got a half mv squared. I've called it c squared here. This is our RMS speed. You could call it v squared as well. You wouldn't get any trouble for this. V is just going to be the square root of c squared. And all we're doing is putting in our numbers, kb being the Boltzmann constant, which again can be found in the data booklet. And we end up with a speed of approximately 1,400. As usual, what I've done here is I've given my answer to a lot of significant figures, in this case 4, and then in this case I've gone to 2 significant figures, mainly because the values here, 3.2, 5.1, they're given to 2 significant figures as well. So any nasty marker wanting to penalize me for whatever reason on significant figures, I think I've covered my back there. So always give me a couple of different values. Okay, we then want to show that the number of helium atoms in the container is 4 times 10 to the 20. Now there's a few different ways you could do this. You could start with PV equals to nRT. We know PV, we know R and T, and we're going to calculate N. And then use the fact that N is the ratio of the number to the Na, which are Avogadro's constant. Equally, you can use another version of the equation, which is PV equal to NKT. Okay, this comes from the fact that N, the number of molecules, is equal to simply the number of moles times the molecules in each mole, and therefore we've also got a relationship between R and Kb. Either is fine. Okay, regardless of whichever way you do it, you should end up with a number around about 3.7 times 10 to the 20. Remember, we are expecting big numbers here. This isn't actually even very big because 1 mole would be 6.02 times 10 to the 23. We've got a very small number here. We've got 10 to the minus 3 moles here, but that's absolutely fine. Okay. We're then asked to calculate the ratio of the volume of helium atoms. Right? I have deliberately circled S here because this is the sticky point for a lot of people. HL students, watch out, because they were looking for the volume of all of the atoms, not simply one atom. So what you're expected to do here is take your number from question B. Okay, and multiply that by the volume of each atom. So we've got 3.69 times 10 to the 23. Okay, make sure you are multiplying your volume of each atom by the number of atoms in there, and then comparing that to the volume of the helium gas, which we know from the beginning of the question is 3.2 times 10 to the minus 6. So generally my impression of this question is that first one bit goes fine, second fine, but then we forget this little point here. We end up with a ratio which does not include the number of helium atoms. So just be careful, okay, when we're doing that. There's a reason that you calculate the number of helium atoms in question B, and that's to use it in question C. It then says, just discuss by reference to the kinetic model of an ideal gas, and the answer to C1, well, there's no C1 here, it's just C, whether the assumption that helium behaves like an ideal gas is justified. So we've got to do something to do with volume, all right? We've got to remember an assumption to do with volume with our ideal gas. Well, we remember that the volume of the molecules in the ideal gas is far smaller than the gas itself, i.e. molecules are points. They do not take up space, however you want to put it. Well, in C, we get a ratio of 6 times 10 to the minus 5, all right? Which is 6 times 10 to the minus 3%. All right, and that very much backs up this assumption. Now, interestingly, this really does depend on your definition of what a small number is. I think this is pretty small. All right, anything less than 1% to me is small. I have seen students say that a ratio of 6 times 10 to the minus 5 is not small enough for this assumption to be valid. Really, I think it is, okay, and that is IB's line as well. I understand that we're always looking for sort of perfection and looking for things to be as small as possible. However, if we're wanting to assume that the ratio, that the volume is low, then really that is a low enough number, okay? So we've got 1 mark there for just talking about the assumption, and the second to show that that assumption is in line with what we've calculated in question C.